Here's a note from Sipser. It's his particular way of doing things, and he's like, look at these two lines here, because they're very important. Okay, so when he says we, Sipser, of course, the textbook author, has chosen to represent these problems like this, these problems, in terms of languages, and we still don't yet understand what he means by that. We're getting there, but we can ask why does he do this? Why does he? Well, several reasons. One is just convenient, because we've already used language format a lot. We're familiar with the language. We're familiar with the terminology of languages, right? It's the current it's the theme, in a sense, of the whole text, using language and the terminology of languages. Okay, so we already have a familiarity using languages and membership, strings of languages, strings within languages, strings that are members of a set, and that set is a language. We're familiar with all that kind of terminology. All right, now as an example, taking a problem and expressing the problem in a kind of language-based format, how to do that. So here's a problem. It's called the acceptance problem for DFAs. Remember a bit of revision. What's a DFA? It's a deterministic finite automaton. And what does that mean? Deterministic. It means there's only one next state each time. Okay. If it's more than one, by definition, it's non-deterministic finite automaton. Right? So here's the problem. Will a particular DFA accept a particular string? That's sort of a special case of this one. Finite automaton, that could be two possibilities. It could be a DFA, it could be an NFA. N, remember, is non-deterministic finite automaton. And what's that? Bit of revision. Non-deterministic finite automaton, you can have more than one next state. Okay? And when that happens, you make a copy of your machine, and you create a branch, like in your computational tree. It gives you the history from state change to state change. When you get a branching, in other words, there's more than one next state, well, one copy of your machine goes down one branch, where the next state is, let's say, the first of several, perhaps, next states. And another copy will go down another branch where the next state has a different value, and so on. So finite automata can be of those two types: DFAs or NFAs, right? Deterministic or non-deterministic finite automata. All right. Well, in this case, it's a DFA. So the problem is, will a particular DFA that you're given, will it accept a particular string that you're given? It could be any DFA in any string, right? Very, very general. And is there an algorithm to answer yes or no to this problem? Right? Okay, now we can bite the bullet, finally. We can give an answer to this question. How do you translate a problem like this? This is an acceptance problem. Does this particular FA accept this string? Right? That's a problem of acceptance. How do you translate that into a language type problem? And here's how it's done. Okay, so introduce a language, and we'll call it A for the language, and subscript, DFA, deterministic finite automaton. And this language, I've got 3 bars here, so by definition, it's a set of pairs, ordered pairs, or if you like, two two tuples. And here are the elements of your set. Okay, and they're an ordered pair. And you've got the angular brackets here. Remember from earlier sessions what that means? It means the angular brackets means it's an encoding, or what was the other word? Representation of data about these things, whatever they are. Talk about that in a minute. An encoding or representation of these things into string format, into one-dimensional format. So you take information about the things you're talking about, like these two things, whatever they are. You take the information about those things and you put them into a linear string, right? It might be a binary string. So you have to decide then how to represent the information about these things into zeros and ones, right? So you have a kind of formatting problem, a representation problem, how to encode the information into a string. Now, the encoding, the representation, that's itself represented by these angular brackets. So you see these angular brackets and you know, okay, so that's an encoding of the information about these things inside the angular brackets, and that information's represented by, encoded by string, okay, linear string, just a sequence of symbols. All right, okay, so what are these two things? B is your machine, your DFA, okay, and W, and it's any string, any machine, any DFA, and your W is a string, any string. So any machine, any DFA, and any string, right? And so you take any machine, any DFA, and any string, and if this machine accepts that string, this machine, this particular machine accepts this particular string, then this ordered pair, this pair, is a member of this language by definition. Okay? Right? Now, can you see now, are you starting to get a feel for where this is going, where this argument is going? So, let's say we are given a particular machine and a particular string. Right? And the problem is, well, here, it's the acceptance problem. Will this particular DFA accept this particular string? Okay? That's the problem. So if the answer is yes, then, think about it, then the pair, the machine and that string, that particular machine, that particular DFA and that particular string, that pair will belong to this language, right? By definition, because this language contains all of these ordered pairs where B accepts W. Okay? So you can turn that argument on its head. If this ordered pair, this machine with this string, if it belongs to this language, then B accepts that string. So you're translating the problem from does B accept W into is this ordered pair a member of this language? Okay? What I've just said is critically important for the whole chapter. So do absorb it, and I'll go over it again in the next session. But it's critical. Okay. Ciao.